Good morning for those of you who are joining in this morning. Good morning, good afternoon, good evening from wherever you're joining us from. We appreciate you being with us. We'll just give folks just a minute or two more to join in, and then we'll get started. So again, sit tight and thank you. While we're waiting in the pregnant pause here, I just want to say that the last few weeks have been very exciting for IWCS. We have really gone into a lot of exciting details on our 2024 conference that'll be in Providence, Rhode Island in October. So we'll talk a little bit more about that at the end of the webinar this morning. But it's very exciting how it's coming together, and we hope you all will participate and be a part of IWCS 2024. So. All right, well, why don't we go ahead and get started? Again, good morning, good afternoon, good evening, and thank you for being with us. My name is Dave Cadu, and I am the CEO and Director of IWCS, and very proud to be bringing our event as well as this webinar series to you as your moderator. A few housekeeping items. One, as an attendee, you're part of a larger audience. So during the presentation, all participants will remain in listen-only mode. And also as a reminder that this webinar is being recorded for rebroadcast. We post these on our website at iwcs.org. And you'll be able to go and see the webinar again or share it with your colleagues. Also, I will be providing contact information for our presenter this morning, so you can reach out to him directly. We encourage you to submit any questions that you have in writing at any time during the presentation using the chat function, the chat panel at the top or bottom of your screen, however it's set up. Once you open the chat on the right of your screen, type in your questions and at the space in the bottom, and then hit the send button, and your questions will be addressed, time permitting, at the end of the presentation. So our webinar series is hosted by the Cable and Connectivity Industry Forum. And today we are honored and welcome Chase Erford from Prysmian Group in North Carolina, USA. Chase will be presenting his paper on materials considerations for laser printed jacket solutions. Chase holds a BS degree in engineering with a mechanical concentration from Campbell University. He joined Prysmian Group in 2022 as an engineer in a functional rotation program. He spent time in fiber optic cable research and development, process engineering, and is now a product specialist for telecom cables in Claremont, North Carolina, USA. So we welcome Chase, and again, thank you for being with us, and take it away.
Hey, thanks, Dave, for the kind introduction. I'm definitely very excited to talk with you guys today, and very thankful for this opportunity to share this presentation again. I originally shared it at the IWCS conference in Orlando this year. It was a great turnout there, and glad to present it again. I was also very happy to be a part of this project, Materials Considerations for Laser Printed Jacket Solutions. So let's go ahead and get into it. So just outline of the talk today, I will go through the story of how we went from the conceptual idea of laser printing to a more robust procedure that actually works. I'll start with some introductory info, then I'll go into what we did, and then what we learned from what we did, and then close up with some conclusions, and we'll have a Q&A there at the end. So with cable laser marking technology, there are a lot of great benefits that comes along with it. One of those being is it has high resolution fine print on small cables or small parts. 1 millimeter text, no problem. It allows for a precise marking on even the smallest of cable designs, and there's no compressive forces, no squished cables from something like old school indent printing. Oftentimes, cable designs that are small or have thin jackets are more susceptible to damage from compressive forces, but lasers, they don't do that. They don't pose that issue because it never actually comes into contact with the cable. And also, laser marked text is much more durable than, let's say, inkjet printed text. You can't just wipe it off with a rag or with some kind of chemical. Lasers permanently mark the surface with high intensity light in such a way that it is not coming off with any rag or chemical. So there are no consumables that these lasers use. They only use you only use light. So there's no solvents like there is in ink. There's no print tape. There's no surface treatment needed. It's all just with light. And then also there are some potential operational benefits, such as improved reliability and uptime to also come with it. But of course, with any new technology you're trying to introduce, there are challenges that come with it. So typically materials with the standard amount of carbon black in them or the light protective agent in the compounds, those with greater than 2.35% of carbon black loading can be difficult to print. They absorb all the light and they don't change color, so they don't do us any good for laser marking. Because of this difficulty to print high carbon black compounds, jacket materials must be modified to get the good print quality we desire. So reducing that carbon black content or the carbon black loading may impact the UV resistance, which is a challenge that we will touch on a little bit more in this presentation. And then lastly, the ICEA 640 cable standard was just modified so that jackets for outside plant applications with less than 2.35% carbon black are now allowed, and this was only just approved in this May. So to tell the whole story behind the concept of this report and this whole project, it all came from the modification of the ICEA 640 cable standard. So these changes to the standard open up the door for more materials to be considered. So what actually changed to the optical fiber outside plant communications cable standard? It's a bunch of words for a standard name, but outside plant cables. What changed was polyethylene cable jackets with less than 2.35% carbon black are now allowed. And then with that, there are some new long-term UV weathering test requirements for those compounds that were also added. So everything beyond this point in the presentation was spurred on by these two changes. So to dive a little bit deeper into what was introduced with the new weathering requirements, so the UV weathering must be conducted according to one of two different cycles, either cycle 1 of ASTM G154 or 155. And those test durations must have a minimum exposure time of at least 4,000 hours. And lastly, maybe most importantly, all the tested jacket materials must retain a minimum of 80% of their original strength and tensile strength and elongation values after the weathering exposure. So this is a little bit more details about the two cycles that you can use. So here are the UV weathering parameters of those two tests from ASTM 155 and 154. So the big difference here are the irradiation sources, one being a xenon arc lamp with a daylight filter versus a fluorescent lamp with UV fluorescent lamp. So the xenon arc lamp most closely replicates natural sunlight, especially with the filter applied. And the exposure cycles are both a bit different, but they're both similar in the way that they both include an elevated temperature and condensation in the mix during the test. So the spectral distribution for the xenon arc captures a broader spectrum of light that simulates more closely natural solar radiation. And then the fluorescent lamp has a narrower spectrum, but a higher concentration of energy that it puts out at a specific wavelength. So for this project, we went ahead and followed through with the xenon arc lamp weathering. So that's what we're focusing on for the rest of the presentation. So looking at both of the artificial light sources on a graph compared to natural light, it's pretty apparent that they dish out very different amounts of energy at the different wavelengths. So usually lower wavelengths are more damaging because they have higher energy. They penetrate deeper into a surface and cause more intense aging. This is both with compound or with skin. This is why you wear sunscreen when you're on the beach or something like that. But at the 340 nanometer wavelength, all three light types have a similar effect, but beyond that, beyond the 340 wavelength, the fluorescent lamp radiance begins to drop off. So the xenon arc lamp, the red line, the big squiggly red line with the daylight filter, is the closest approximation to natural sunlight. So of the two options for UV weathering, the xenon arc lamp light source is the easiest to develop correlations to natural UV exposure because the test is designed to simulate the spectral distribution of natural sunlight. It's trying to replicate what actually happens if you stick a cable outside for a long period of time. So here's that same graph, but zoomed in just a little bit. And this is comparing increasing intensity versus increasing dosage. So there's a reason why we have the 4,000 hour test duration, which it takes a long time, but there's a reason for that. So you can increase the amount of time or the dosage that a specimen is exposed to the normal light intensity, or you can increase the intensity or the brightness of the light, so you can decrease that time that the specimen is exposed. But it doesn't always work out the way that you expect it to. So if you want to increase the UV dosage, you can increase the amount of time, or you can increase the intensity. But if you increase the intensity, I may not always have the desired result. And I like to think of this, to visualize this example with the egg in an incubator example. So if you leave an egg in an incubator with a normal heat lamp, in about 20 days, you have a chirping little chick. You get what you expected. But if you get a little impatient, you want to speed up the test, if you think increasing the intensity of that lamp, increasing the temperature of that heat lamp, in about 20 days, we'll just have a hard-boiled egg. So you can't just rush these kind of tests. That's why we have these long test durations. It's kind of like a cake. You can't just throw a cake in an oven and expect it to cook faster if you increase the temperature. So just a good way to visualize our reasoning behind the test duration. So here is a map that shows the various UV dosages in kilolanglis across the globe. And the UV dosage represents the amount of energy a surface receives from electromagnetic radiation or sunlight or light. And this map is showing how it varies so much across the globe. And this these numbers are based on more things than you can count, but there is dramatic differences between where you're at on the globe and the amount of sunlight a place receives. So for this map, 200 is about the highest you're going to get, and 60 is the lowest. And for the test that we're performing for this, or we perform for this test, I believe the goal was to achieve the natural sunlight exposure similar to that is received in South Florida, which is about 140 on this chart. So here is a comparison, or a comparison between some weathering of natural sunlight from South Florida versus xenon arc, and this is tested with between 3 different studies of 14 different polyethylene compounds. So you have South Florida on the left and xenon arc on the right, or on the bottom, and with a little bit of variability, you can see that the controlled xenon arc weathering closely matches sunlight aging. So it's kind of backing up why we're choosing the xenon arc weathering versus the other light type. So now let's talk about what we did and how we did it with our experiments. Like I've said a couple times already, we chose the xenon arc weathering because it most closely matches natural sunlight. We like its wider spectral distribution and its degradation rate because it most closely replicates South Florida light exposure. So to introduce the actual jacket materials, the compounds that we are testing, we have 3 testing side by side. So we have a control, which is a widely used, very common, low shrinkage, high density polyethylene. And then we have 2 other laser specific high density polyethylene compounds with decreased carbon black content, denoted simply as laser compound 1 and laser compound 2. So each of these laser compounds are expected to be a nearly 1-to-1 replacement of the widely used control, even with their lower carbon black and their UV resistant packages. So we see that they have very similar densities and very similar melt flow at the typical melting temperature. So this is why we expect it to be a drop-in pretty much for the typical control sample. So here is the actual laser that we used. We used a 50-watt fiber laser with on-the-fly marking capability, using a light wavelength of 1064 nanometers, which is very common for this application. And then the fine marking is achieved with a line width of 0.012. That's the actual width of the light itself. And for safely marking cables, there's some auxiliary equipment needed, like cable guides or light guards, and then also proper fume extraction. And this fume extraction is especially important for PVCs or other chlorinated compounds. I know that this is outside the scope of this topic, but I felt like it was an important side note for this discussion. So on to the results. How did our materials do? Well, let's find out. So we started with some stress crack resistance tests. We tested very small samples and with controlled imperfections, little cuts down their length. We bent them to harsh angles and we aged them for 1,000 hours in an oven in dry heat and in a heated solution. And all the compounds passed the environmental stress crack resistance at all study conditions with flying colors. And you can see the test configuration there on the right with all those lovely little samples in the trays with the controlled imperfections. And let me tell you, those are very fun samples to bend and get into those trays. Things we do for science. But we also tested tensile and elongation for various cables made at different line speeds. So we have some sample cables that we did at line speeds from 30 to 100 meters a minute, and we aged those samples for 7 days and at 110 degrees Celsius, and we tested the mechanical properties for both the aged and the unaged. and they are conformant to ICEA 640 requirements for all the materials. There was little variation to line speed and thermal exposure that we noticed in these tests. And well, sorry, there is a little bit of variation of the tensile and elongation performance here. And the reason why we have that variation is because it's not the UV stabilization or the lower carbon black. It's not the change of the compounds, but we think it's more of a result of the residual material stresses due to the extrusion process, or maybe secondary crystallization after thermal exposure. So this variability is something that may also be a result of the elevated temperatures during the UV aging, but that's a topic for another study. So this is looking at that same info again, but in graph form. So we can see that the tensile performance of the laser compounds matches or meets the expectations, and it performs similarly, if not better, than the fully compounded control sample. So looking good there. So we also tested jacket shrinkage from those cables that we made at the various line speeds, and the jacket shrinkage results for both laser jacket compounds was low and showed very little sensitivity to line speed. And these results are well below the ICEA 640 requirements at all the line speed studied. Still looking good. So this is to discuss print quality. The line speed is not actually what affects print quality, but rather marking speed. So there's very little difference in the actual marking quality with increasing speed. As you can see there on the right, there's not much change between the 50 and 100 meters per minute samples. But the three main marking parameters are marking speed, which is how fast the laser actually traces each one of the letters; the frequency, which is how often the laser beam cuts on and off to trace each one of the letters; and then the pulse length, which is how long each of those pulses are on for as it traces the letters. So you see there on the bottom left as well, there's small text on a small cable. It also looks really good. So it's just a good example of small text, small cables. So here's print durability after of a 100 meter per minute sample after harsh abrasion. So the laser marked text demonstrated excellent durability, even to rough abrasion from a Scotch-Brite scouring pad. And you can do this with ink printed cables, but you often have a hard time reading the text after such harsh abrasion. And you can see this laser printed text is different because the laser actually vaporizes the surface of the cable, which permanently marks the surface, and it cannot just be rubbed off. It takes quite a lot of effort, as you can see in the picture. And then here are the most exciting results from the study. We have the UV aging results from the laser compounds. So we UV aged both of those compounds for 4,000 hours, and we tested their tensile and elongation properties. We have the tensile test on the left and the elongation on the right. So the laser compound 1, it performed nearly identical to the control up to the 2,000 hour mark. And performance did begin to decrease some, but is well within the ICEA 640 specifications at the 4,000 hour duration. And then the laser compound 2, it showed some earlier reduction in properties, but we believe that this can be improved and is partially related to process sensitivity. But the main idea, the big point here is that both laser compounds, even with their reduced carbon black content, meet the new ICEA 640 standard requirements. So this is the same info, but in table form. Laser compound 1, it has those good retention numbers in the earlier parts of the test, And then laser compound 2, it had a little bit more significant change in tensile performance, but is ultimately passing and meeting the new ICA 640 requirements. So to wrap up this presentation and this project, we tested 2 laser markable high density polyethylene jacket compounds, and we tested the laser marking performance of them against the new ICA 640 standards for outside plant cables. So the print marking and the durability were excellent for both compounds. The environmental stress crack resistance of the compounds was also excellent. And the mechanical properties and the shrinkage of the extruded jackets are essentially identical to current low shrinkage jacket compounds. So conformance to the new long-term UV weathering requirements in ICA 640 is possible with properly formulated and stabilized laser markable jacket compounds. So looking into future work that we might be looking into, we have some longer term aging that is going beyond the 4,000 hour mark, and that is ongoing so we can better understand the weathering performance of these new compounds. And then we might also investigate the things such as the thermal exposure during the UV weathering, the increased temperatures during that, and then also process variability on the initial and UV aged tensile test results. We'll be looking into that as well. So that pretty much wraps up my presentation. I appreciate your attention during all this. So I'll send it back over to you, Dave.
Chase, thank you so very much. An excellent presentation. Again, we appreciate you bringing this information, this great work to the broader audience. And I remind participants to put any questions that you might have for Chase in the chat, and I will ask those of him now. But to get started, Chase, were there any specific safety considerations or precautions related to the use of laser equipment during the evaluation of these compounds? You're on mute. There you go.
Sorry.
There you go.
The laser that we use is a 50-watt fiber laser, and it is deemed a class 4 laser. So any light that bounces off something and gets in your eye, that can be properly dangerous. So you have to have proper light shrouds around the laser itself, and also you have to have good fume extraction. These things, there's sometimes there's some smoke that can come off the cables. I mentioned in the presentation, like PVCs. If you mark on those, there's toxic smoke that comes off. That's not stuff that you want to breathe in. So proper fume extraction is needed, and it's not like smoking up your whole building. It's just a little bit,
Sure.
But it's definitely something to consider. And yeah, those are the 2 main ones. You have to have you sometimes have to wear glasses, but definitely class 4 lasers are serious things, and you have to take them serious.
Good. How does the laser marking performance of these new compounds compare to conventional compounds, especially in terms of clarity, readability, that kind of thing?
So yeah, just like we tested we have a control material that we tested in all these different tests we did. We laser marked it as well. We got some samples and tried to laser mark it, and honestly, you can't read it hardly at all. I mean, these new compounds with the lower carbon black, they receive the light and actually mark on the surface, whereas the higher carbon black stuff that we use for the control, it absorbs all the light, and it absorbs the light, but it will still melt. So you can sometimes see a little bit of a trace of the words that you're marking, but honestly, you can't read it hardly at all. So there's no performance on those high carbon black compounds.
Great. Are there specific steps for preparing materials for laser marking, such as cleaning or any kind of surface treatments, applications, coating applications, things like that?
For this, no, not particularly. Nothing crazy. You have to make sure your surface is clean, of course, and it can't be wet. But that's with anything. But there's no surface treatment needed. This is something that you can extrude right onto your cable, and it pretty much goes through no problem. There's other printing methods where you might have to treat the surface, or sometimes with metals you have to heat it, or you have to do whatever. But for this, as long as it's dry, as long as it's not moving around a lot, and clean, it'll pretty much mark every time flawlessly.
Right. Is the line speed potential to be up to 1,000 meters per minute level? And secondarily, in case of any kind of printing error, is it pretty much impossible for remarking? And for inkjet, you can wipe them off and remark,
Mhm.
or how would you address that?
So for the 1,000 meters a minute, uh, I have not researched into the speeds that quite that fast, so I can't really speak on what else is on the market. Um, but certainly, that would be excellent. Going that fast with the laser, that's absolutely outstanding. Um, and the second part of that question was what?
It was, if there's a printing error, is it pretty much impossible for remarking, since the laser mark is more intrusive than a surface inkjet type of mark?
So it depends on what you want. Sometimes if or it depends on customers, depends on internal requirements, whatever. You might have to strip it and rejacket it. But or you could send it back through and print it with a different color. That's something that's also possible. But I don't know the typical requirements for that. But I do know that there are some options on the market for uh, cameras that you can install after the print is, so like the printer's here and then the camera's beyond it, and it will read the text and look for errors as it's printing, so that you can catch an error if one happens very quickly, and it's tied to the laser and it will cut it off right when it notices the error, so that you could go back and correct it as needed.
And minimize the continuation of that error.
Correct. Yeah, yeah.
Yeah. Was the durability only tested with a scouring pad? Have you considered actually pulling the cable through a dirty duct, for real world testing?
We haven't quite gotten that far as of yet. We have some other standards that I can't quite recite off the top of my head. We tested it with some less abrasive measures, and then we also tested with a Scotch-Brite pad. But I also we have a standard where we have go across it this many times and yada yada. But then
Mhm.
I got the scouring pad with my own sample and just
Right.
I mean, scrape the mess out of it, and
Hmm.
it still was able to be read. But no, we haven't gotten to the point of actually testing beyond that.
Yeah, so that may be something for the future to
Yeah.
look at various different environments and things like that. Have you tested any PVC compounds? And if so, is the same requirement of 2.35% carbon black still applicable?
For that one, I don't know enough to properly answer, but that's not quite in the scope of this presentation. But I would definitely take it offline if someone wants to.
Yeah, and I will be providing Chase's contact point at the end here. So if you want to reach out to Chase after the conference or after the webinar, you can. What are the aging mechanical behavior at the laser printer area with respect to the non-printer area, is laser printing deteriorating? What are there any differences in that manufacturing process? Not quite sure I
So
understand the question.
uh, I think I got what they're saying is
Mhm.
does the laser affect how strong the jacket would be? As far as
Good
what
point.
we've
Yeah.
done, I don't want to talk about anything like that. But uh, I will say that the laser, when it's marking on the cable, it only marks but a few microns deep and is not permanently, it's not cutting through the cable. You know, when it's moving at a certain speed, you can control how much power it's dishing out and how much light the cable is actually receiving. So you can control how, I guess, deep you're burning into a cable. But you know, properly marking a cable, you're only marking just the very outer surface. So I wouldn't expect it to catastrophically change any sort of mechanical properties. But that is not something that we tested for this paper.
Okay. Um, and again, not sure if you've expanded it to multiple materials, but besides the carbon black level, are there any other restrictions to particular polymer types? You know, PVC, polypropylene, uh, flame, halogen-free flame retardant materials, things like that.
I don't quite know. I don't know enough about what else in the standard. We mostly focused on polyethylene cables for this. That's, I think, the focus of the standard changes we had for this. So
Hmm.
I would definitely be willing to get with the right colleagues to answer that question offline if you want, or if the question asker would like.
Sure. And I think you know, laser printing is becoming well used throughout the industry and throughout many applications. So I would imagine it's just slightly different additives, slightly different treatments, and but I'm pretty sure it'll be able to be used in most materials. How is the impact of cost and maintenance of laser printing versus regular inkjet? Is it significantly different?
I would expect so. I don't have any numbers to share, obviously, but uh, the laser, the maintenance you have to do to it from the manufacturer, they said you just have to wipe the lens. And I think that is absolutely astounding. They say it can last up to 100,000 hours, and that's what they promise, but that's not its actual lifetime. It can go much beyond that. So 100,000 hours, we're only really having to wipe off the lens. That's pretty awesome. I think that's pretty low impact financially with that maintenance versus, you know, other, you know, using ink printers or using uh, larger printer types. I know this thing is really small and it just has a lens that's like, you know, it's that big. It's pretty small. But you have ink, that stuff. If you turn it off or if you leave it in there too long, you know, you think about your printer at home. If you leave the ink cartridge in there too long, it dries up. You know, same thing happens with the inkjet printer for cables. You know, that stuff, it clogs up and then you've got a mess to clean and happens
Yep.
over and over and over again. And who knows? So as long as you keep the
Mhm.
lens clean, it's pretty low maintenance.
Good. Um, are you going to look in the future at different jacketing colors and the legend colors? You know, any kind of, because obviously you need to have the right kind of differential between the legend and the jacket in order to have good readability.
Mhm.
Yeah.
That's a good idea. That's not something that we're doing future work on. You know, we're sharing what's on the screen. That's what we're doing right this second. That's Those are good ideas. Definitely something to consider, and maybe that's a topic for a future discussion. Who knows?
Good. And I think you mentioned this, but what was the carbon black percentage for the various samples that you tested? Did you look at a range, say 1% to 2.3%, and find, you know, sort of an optimum?
No, we don't have a specific carbon black contents of the samples that we have. That's not something that we can share right this second.
Right. And again, fairly qualitatively, but how good is laser marking versus regular inkjet? Is it more difficult to read? Is it clear? I think you showed some good pictures of pretty good clarity.
Mm-hmm.
But what's your impression qualitatively between the two?
I think it's absolutely excellent. You can get white on black contrast with these cables, and the samples that we showed in the presentation, they were single raster, like a single trace of a line or of a letter. You can also do a filled letter, so it's a little bit thicker. So if you want to get more contrast or bigger letters, you most certainly can do that. You can put any font you want. You can print a picture on there if you want, and it'll be white on black, but you get the point. It looks really awesome. An inkjet, a lot of times those are like dot matrices or dot matrices and stuff. This one it looks like a real picture, so it's pretty awesome.
Good. I want to thank everyone for putting your questions in the chat. A lot of questions, which is a testament to the great presentation that Chase has been giving us. We have time for a few more. Here's a good one. Does the laser have to be positioned prior to the cooling trough, or can the jacket be cooled, air wiped, and then printed? I mean, where in the extrusion line is the optimum place to put the laser printer?
I would think the optimum place would be at the very end, just before you wrap it up or send it up to the next step. It's definitely, it's got to be a solid surface. It has to be a smooth surface, and it has to be dry. So definitely after the cooling trough, it would definitely need to be printed there. Um, so uh, and you have to position it correctly. It's got a little bit of a wiggle room. It's light, so it's got a focal distance you have to be within. And lasers, there's 2 to 10 millimeters of wiggle room, depending on the laser you have, of travel that the cable can bounce up and down or move left and right. And it's, as long as it's dry, it'll do what it's supposed to do on the right material, of course. But yeah, that's something that we did test. Is we bounced it up and down, see what would happen, moved it left and right, see what would happen. And as long as you're within the focal distance of the laser, it will mark.
Yeah. What's I don't know if you have the exact numbers, but if you want to share that, but what's the maximum line speed that you have run with good results? I mean, just in the scope of this test, this program.
For this, we did for this specific project, we got up to 100 meters a minute, and it looked really good. And anything beyond that or below that, it's up in the air. But the 100 meters a minute sample that we did do looked very good, and it looks good all the way down to sitting still. So you can mark it when it's sitting still. 5 meters, 100. It looks pretty good between there, and that's what we shared earlier.
There are a few specific questions on various different applications, and again, I encourage those questions to be asked directly of Chase offline. Just one or two more. I'm using laser-based HDPE, but the material cost is 30 to 40% higher than the regular compound. How does this impact on actual cable pricings? Are there adjustments need to be made to the price point using laser marking?
This is probably a discussion that will be needed to have elsewhere, but that's that in that case, 30%. That's definitely a significant change. But I can't really talk too much about that. That's not my area of expertise.
No, it's a good question, and obviously with every part of improved quality control, it comes at some cost. So, are there any concerns that you have about the depth of penetration having any effect on the insulation, and how much trial and error to figure that out. Clearly, you don't want to create some voids that might cause any kind of either cracking, mechanical, or even other transmission types of errors.
Mhm.
And any
Yeah.
depth issues?
We kind of touched on this a little bit earlier, but you can control the depth that you want. At the speed, at any speed, you can turn up the power, turn down the power, change the frequency, change the pulse length. It all comes down to how long is the laser on a specific point. That's the depth you're going to get. So if the laser is zapping on the same spot for a really long time, it could cut through the cable, if you leave it there long enough. But most of the time it's just zapping across the surface super duper fast, faster than the human eye can even see. So the actual depth that the laser is penetrating is very minimal, and you can control that, of course. And I mean, you can measure that as well. Doing a cross section of one of those spots, you can measure the actual depth, because it's got a different color, and it's visible. But as far as that being a concern for this project, not a topic we're discussing this time.
Great. Well, certainly good work for future projects, and we hope that you'll include those as abstracts and presentations in future IWCS events. We certainly look forward to hearing more as this technology evolves. But again, thank you, Chase, for this really interesting and important topic. Again, I think all the questions that we received from the audience, they were very much engaged as well in what you had to say. So thank you. You can see on the screen here the contact points for Chase, should you wish to contact him after today's event. I know that there were some questions that we unfortunately couldn't get to, but if you want to reach out to Chase, please feel free. Each of these IWCS webinar series events are recorded and will be archived on the IWCS.org website. Normally takes a week or so to get them up there, but certainly feel free to go back and revisit the presentation, and also share it with your colleagues that you may have in your own supply chain. The webinar series will conduct further technical paper presentation webinars, as well as some sponsored company events each month. Our next scheduled technical paper webinar will be on Friday, December 15th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for that event. Please feel free to share that announcement with your colleagues so that they can join in and register as well. It's important that we all recognize and thank our IWCS partner sponsors who contribute greatly to the success of our Cable and Connectivity Industry Forum, both in terms of content, as you saw here from Prysmian, but also their strong leadership and generosity financially, so that we can bring these important technical innovations and information to you and our global community. So again, thank you to Prysmian and the other partner sponsors that are so vital to the success of your Cable and Connectivity Industry Forum. So thank you. For over 72 years now, IWCS Cable and Connectivity Industry Forum has been the recognized leader in showcasing these new technologies in cable and connectivity products, processes, applications. And as I mentioned earlier, we're really excited about our 2024 event. We're starting to put together a very strong concept for the conference, and you'll be receiving soon enough the call for papers, and take a look at the types of subject matter that you might be able to participate and present in as well. We'd certainly love to have you in Providence. The 73rd annual Cable and Connectivity Industry Forum will take place on Monday through Thursday, October 14th through October 17th, 2024. And we will be returning to the Rhode Island Convention Center in Providence, Rhode Island, USA. So please watch your inbox, social media, and of course our website to learn more as the exciting information becomes available. So please visit IWCS.org for more event details. And again, I want to thank Chase, and I want to thank you all for participating today. This will conclude today's webinar event. I wish you all a fantastic weekend. And for those of you in the North America, USA, happy Thanksgiving next week. We're clearly into the holiday season, so enjoy. Take care.